In this video, we are going to do some examples of sinusoidal curve fitting. So basically what that means is we're going to look at some real-life data that fits a sine wave. Alright, so we're looking at number 1 here. So let's go ahead and read through that. It says, the following data represents the normal monthly precipitation for a certain city in California. Draw a scatter diagram of the data for one period and find a sinusoidal function of the form y equals a sine times the quantity omega x minus phi, that's a phi symbol there, plus b that fits the data. Draw the sinusoidal function on the scatter diagram. Use a graphing utility to find the sinusoidal function of best fit. Draw the sinusoidal function of best fit on the scatter diagram. Alright, so we're going to do kind of a combination of graphing utility and looking at how to find some of these values just from the data. So the first thing we need to do is plot all this data. Alright, so let's see if I can get this pen working here. Our x values, our inputs are going to be these months. So we can just label these. Uh-oh, I don't want that to get bigger. Hold on. Okay, hopefully that looks better back where it was. Alright, so we've got month 1, and then we need to do, we could just fill these in here. So you guys do this with me, and then we're going to plot this data, see what it looks like. 1, 2, 3, 4, 5, okay. Alright, then on the y-axis, that's going to be our precipitation in inches. Goes up to 6. I guess we'll just make each of these worth 1, because we don't have enough to make them worth a half. So this is going to be a little bit of, just doing the best we can, because these numbers, we're going to be estimating, right? So on January, we've got 6.06. It would be nice if this had some grid lines in it, but we get the idea. Oh, I'm going to need a darker pen. Let's see. Let's do purple. Okay, let's try this one. So 1, 6. That's pretty good. All right, so 2, 4.45. 3 is a little bit lower than that. Again, just estimating here. Five is 1.27. 6 is about a half. 7 is lower than that. 8 is back up to about a half. 9 is almost 1. Oh, that last one doesn't look like a half, does it? Close enough, right? 10 is 2 and a quarter. 11 is 5.21. And 12 is just a little bit above that, 5.5. Okay, so you can kind of see a sine wave pattern here. And I'm going to show you how to do this with Desmos, but I just want to look at how we might estimate some of these values in the equation. So let's look at the first value here. Let's look at amplitude. Alright, so we know that amplitude is the distance between sort of like the middle of the graph and the top, or the middle and the bottom. So in other words, if you took the highest point and the lowest point and found the distance between those two, if you took the high point minus the low point and then divided that by 2, that's going to be a pretty good estimate of your amplitude. So for the data we have here, our highest value is 6.06. Our lowest value is 0.17. And so if we divide that by 2, let's see, what do we get? I think we get about 2.945. So that's a good estimate of the amplitude. When the more the data doesn't look like a sine wave, the more you could get some different answers for this. There's some very complicated algorithms that We'll do the curve fitting in graphing utilities and things like Desmos, but it should be pretty close to 3. All right, let's look at the vertical shift. So let's look at this B value. So the B value, you know, that's going to be like how far it was shifted up. So basically sort of like where your new x-axis would be. All right, so what you're really looking for here, a way to think of it, is the midpoint between the high and the low. I'll erase these marks here in a minute, but if I think about, okay, about here's my high, about here's my low, so my sort of new x-axis should be in here somewhere. So I need to figure out what this number is. Well, that is halfway between the high and the low, right? So to figure out the B value, I'm going to take the highest number I have plus, to find the average, the lowest number I have, and divide by 2. That'll give me the average of those two numbers. So again, the highest number we have is about 6.06, the lowest number, and then divide by 2. And that comes out to be about 3.115. Alright, I'm going to erase these ugly marks here. So again, you're finding the average. That's why you're adding them. Alright, so the next thing we're going to look at is the period of the function. And we know the period of the function has to do with this omega value here. When you're dealing with a real-life situation, the period of the function is going to present itself sort of in the story problem. So we've got this monthly precipitation in a certain city, and this is affected by what time of year it is. And we can kind of see from the graph it looks like it makes one sort of a period here. Now, this looks like a cosine function because it's starting high and going high. But if you think about shifting, every cosine function can be written as a sine function. Like, you know, if you take sine and shift it over, you can get cosine. It's all the same shape. So most of the time when we do curve fitting, we do sinusoidal curve fitting, although we absolutely could do a cosine curve to this as well. All right, so we know the regular period for, say, some kind of a yearly situation, this is going to be 12 months. Then it's probably going to start over again with the precipitation. We don't have 2 or 3 years of data here. We just have 1 year of data. But we're kind of expecting that, okay, here's what happens to the rain, and now it's January again. So we're going to kind of hit the same thing again, or at least get data in that way. So we know the period is 12 months. So we know to find omega, we're going to take the period and do 2 pi divided by omega. Alright, so I'll do my little slick switch the 12 and the W, or omega business here, to solve for omega. And we get that, which is pi over 6. Alright, and an estimate for that, I just want to write this estimate down because we're going to go over to Desmos and see what Desmos has to say, is about 0.52, I think. Just punched it in the calculator. Okay. Now, if we were going to try to finish this by hand and figure out what phi would be right here in order to get our phase shift, we would need to plot the sine function that we have with just these 3 values and then see how far we'd have to shift it to get it to match up. There's really no great algebraic way to figure out what phi is. So what we would do is we would say, well, so far we've got, without any shifting, y equals a times the sine of omega x plus my vertical shift. Then I would plot this on this graph and see how far I'd need to shift it left and right to get it to better match this data. Well, you know, that's kind of a pain. So now we're going to go over to Desmos, and I'm going to show you how we could do all this with Desmos, which kind of begs the question, well, why wouldn't you do it all with Desmos in the first place? The answer is you probably would, okay, but I want to show you guys where, you know, what these values mean on the graph and how it's very easy to figure out the amplitude. and the vertical shift, the up and down shift, and then the period from data like this. All right, so if you can, maybe go open Desmos. I'll give you a second to do that. Or maybe pause the video and go open Desmos. That's probably smarter. All right, so once you have Desmos open, I want you to input this data into a table. So the way you do that is you come over here to this plus sign. All right, and you click the plus sign, and then you have the option for a table. All right, so now put all the data in for the table. I'm going to pause the video and put all my data in. Maybe you could pause it and put your data in. All right, so I have all the values in my table here, and we can see that the graph of those dots is over here. Kind of looks like our graph. Not too bad for our graph there. All right, now in order to, and you could change the settings here if your graph's off so you could see the points. If you can't see the points, make sure your scale is correct. So to get Desmos to tell me what the sine of best fit, the sinusoidal curve fitting, is going to be, we are going to use the values in this table. So and just create our equation, our y equals a sine, all that business. All right. So instead of saying y, though, we have to say y1. And the reason we have to say y1 is because we are telling Desmos to look at these values here, y sub 1. And if you just type in y1, it'll do a subscript. Now, instead of equal to, we're going to use a little, I think it's called tilde, and it's right up by the 1 key. It looks like that. Should be just to the left of your 1 key. And then we're going to type in a sine of, and instead of using the Greek letters, I'm just going to use, I don't know, maybe y'all use M for omega. Use whatever you want. Now, the next thing is x1, right? So, x1, be sure to put the, oh, we already got a sine wave here. Let's see, let's go back over here and look at this real quick. Minus, all right, so here we're doing omega x minus phi plus b. Let's go back over to Desmos. So, minus phi, I'll just use a p for phi. Hopefully it doesn't think it's pi. It shouldn't. Let's do, I'll use c. Alright, close parenthesis, plus d. Alright, beautiful. So now we have a sine wave here. Scroll this up a little. So it's fit the curve to our data. It's given, Desmos is telling us what it thinks the sine of best fit is here. Now notice down here we've got our numbers. So it's telling us A, our amplitude is 3.15. All right, what did we get from the graph? We got 2.945. That's pretty close. All right, it gives us a pretty good idea. The amplitude's around 3. All right. The next thing we got is, it's got some funky negatives in here. Let's go to D. So our D value is 3.18 from Desmos, which is the up and down shift. And we came up with 3.115. So that's pretty close. That's good. Now Desmos has given us a negative omega value here, which is getting into some tricky stuff here. You'd have to use you'd want to factor that -1 out of this and then remove it to the front here of the sine in order to get some even and odd property. Using even and odd properties, sine is odd. So the sine of negative something is the same as the opposite of sine of something. Right? So basically it's like shifting it in a different direction and then flipping it over. That's a little complicated to show here. Let's put our function in and see what it looks like. So remember, we got y equals, let's say our a value was 2.945 sine of, and then we got pi over 6. We could literally put in pi over 6 times x1. Now, whoa, that's a mess. Interesting. Oh, no, I don't want x1. Sorry, just x, right? We're not referring to the table. And then I'm going to put in a slider, all right? I'm going to put in plus c, because we never figured out our phase shift. And then, but we did, or minus c. Sorry, let's do minus c. Minus c. And then let's do, we had our vertical shift was plus 3.115. All right, so what I'm doing is I'm putting in these values over here. I'm basically putting this in. but then I'm putting a plus C for a minus C, excuse me, for a slider, so we can move it around and get it to fit. See, ours looks pretty good. All right, Decimals is in black, ours is in red. Ours looks like it could use a little shifting. Where'd my slider go? Why isn't it telling me to add a slider? Let's try. There we go. Capital C. I don't know. Sometimes technology's finicky. All right, so we're going to move this back over. When C was 0, if I could set C to 0, that we can see if I set C to 0 here, it's going to need some shifting in order to match up. So I can just move this along over here and get it to where I think it looks the best. Let's turn this one off so we can. Where do you think it looks like it's fitting the data closest? You know, it's kind of a guessing game. Maybe about there. All right, so this would be another way that we could write this function here. Now remember, pi over 6 was actually 0.52. Let's take this out and make it approximately 0.52, I should say. So that kind of fits up with where they got this negative 0.46 business. All right, I want to talk to you guys a little bit about this negative omega here, because we haven't talked about even and odd functions in class. So let's go back over here. Let me make a new slide. Get rid of this. Okay, so even and odd properties. So since sine is an odd function, we know that the opposite of f of x equals f of the opposite of x for odd functions. So an example of odd functions that you knew before was y equals x to the third, or f of x equals x to the third. This has some symmetry about the origin, 180-degree rotation symmetry. So see if I get this. Is kind of look what like x to the third looks like. If I rotate 180 degrees around this point, it's going to land back on itself. That's how the graph of an odd function looks. All right, so it has this characteristic here, right here. So if we took, let's say we let x equal 2. So what this would be saying is if you did f of 2, which is 8, and you took the opposite of that, f of 2 is 8 up here, okay? That would be the same as if you did the f of negative 2. In other words, negative 2 to the third power. That's negative 8. Okay? That's a characteristic of an odd function for any value of x. So for sine, if we have sine of negative x, that's exactly the same as the opposite of the sine of x. Actually, let's go to decimals and just look at that real quick. Let me turn some of this stuff off. I won't turn the table off. But let's look at y equals sine of negative. Let's do negative sine x, because you know what that does, right? What does negative sine x do? It flips the sign over. So usually sine is like a hill and a valley. But if it's negative, it's going to flip it over and make a valley and a hill. Now let's look at y equals sine of the opposite of x. That's the, boom, right on top of it. See? There's the purple one. There's the blue one. It's the same exact function. So this is what you would do if you had a graph that, an equation that you wanted to graph that had a negative x here. You don't really want to think about a negative period, right? That doesn't make a lot of sense. So if you had something like y equals negative sine of negative 3x, and you wanted to graph that. Well, you know this affects the period, but negative period doesn't make sense. So you use the property of odd functions. You bring the negative out in front like that, and then you just graph that thing. And then you say, okay, the period is 2 pi over 3, but because of this negative, I'm going to flip it over. All right? So now, let's erase all this stuff. Why is it doing that? So if we look at the equation that Desmos gave us over here, I'm going to look at, for our sinusoidal curve fitting, Desmos gave us this equation right here, okay? You can jot these numbers down if you want, or pause it and jot them down. I'm going to take these numbers and write the equation over on the other screen. So Desmos gave us y equals positive 3.15. I'm just rounding to the nearest hundredth here. Times the sine of negative 0.46x minus a negative 1.59 and then plus 3.19. And when we did it, we came up with, when we did all this business right here, we came up with us y equals 2.945 times the sine of 0.52, that was our pi over 6, x minus, and then if our shift, I don't need you, go away. Our shift that we did, where was it, right here, was about negative 1.2, so minus negative 1.2. Looked like a pretty good shift. Minus negative 1.2 plus 3.115. Okay, so I want to show you guys how these compare to each other, even though they're written a little bit differently. So with Desmos, we could see here we've got this negative omega value. So what we're going to do is we're going to factor that negative out and bring it out to the front. I'm going to take 2 steps to do this. So I'm going to pull the negative out of this. That's a plus. When I pull the negative out, it's going to be negative plus 3.19. Then by odd functions, I could take this and pull it out here in front of the 3.15. I'm using the fact that sine of negative 0.46, all that business, and I'm going to change it to negative sine x. Okay, so that's going to give me negative 3.15 sine of 0.46x minus 1.59 plus 3.19. Alright, so what Desmos is doing is, because this is negative, it's shifting to the right. Now, it's not shifting to the right 1.59 units, because remember, to get the actual shift, what you would have to do is pull out the 0.46 and then take 0.46, 1.59 divided by 0.46. Let's see, minus, let me do that real quick. Alright, that's about 3.46. 3.46 plus, do I need another set of parentheses? Yeah, I do. 3.19. Okay, so if I was graphing this one, thinking about what this means, this is telling me that I'm shifting to the right 3.46 units, and then this is telling me that it's flipping upside down. Now let's look at what ours is doing. Alright, we've got a minus a negative here, so that's going to make a plus. 2.945 sine. Now I'm going to go ahead and factor out this 0.52, and that's going to be a plus. Alright, what's 1.2 divided by 0.52? Alright, that's about 2.31. Another set of parentheses, 3.115. Okay, so ours is saying, you know what, we're going to shift to the left 2.31 units. And then we're going to not flip it over. Okay, now I want you to notice, remember our period was 12. Look at what you get if you shift to the right 3.46 versus the left 2.31. If you add these two numbers together, it's pretty darn close to 6, which is half a period. Okay, so if you shift to the right and flip it over, or shift to the left and don't flip it over, you're going to kind of get the same shape. Maybe mess with that a little bit and visualize it. So these two equations, you know, we saw from Desmos that they were pretty much the same equation. Just looking at the graph, we could see that. Here's Desmos' equation in black. Here's our equation in blue. All right, well, why is that? So I'm trying to help you see, you know, why those equations look so different. Why is that? You know, well, this one, like I said, is taking a normal sine function, original sine function, a plain old sine function, shifting it to the right and flipping it over, and we're shifting to the left and not flipping it over, and you can end up with the same kind of a shape there. All right, so that's a lot. That's good. You guys are going to do the other two. Let me show you one more thing with this even odd business that I wanted to show you guys from class. Cosine is an even function. So remember, with an even function, the property is f of x equals f of negative x. And even functions like cosine are symmetric about the y-axis. So I could take this and reflect it over the y-axis and get that. All right, another example of an even function is y equals x squared, our old friend the parabola. If I take this and reflect it over, I get that. So that's an even function. So that means if I were to ask you guys to graph, say, y equals the cosine of negative 2x. Well, since cosine is even, that's exactly the same as y is cosine of 2x. So basically, you just drop the negative. Now, why can you do that? Because cosine is even, and it has this property. Let's go take a look at that over here on Desmos just real quick so you could see that. Well, let's get rid of our table, or at least hide it. Okay, so if I put in cosine down here, cosine x, there's our nice friend cosine. Now let's put in cosine of negative x, exact same function. See? So if you had something complicated like cosine negative 3 times the quantity, and we'll shift it over a little bit. Let's hide this one. Okay, and you wanted to graph that by hand, you could basically just drop this negative 3 here and do 3 quantity x minus 1. See, exact same function. Oh, let's put it, that's green, kind of hard to see. Let's make it orange. Orange, purple, orange, purple. Looks like weird color. Okay, same function. Now be careful. If I asked you to graph, say y equals negative 3x plus 3. You can't just drop this negative right here. Let's go over here and look at this. Negative 3x plus 3. I'm running out of space here. Let's maybe get rid of some of this stuff. Okay. So, grab a pen. Uh-oh. Let's say you had cosine. I think I had negative 3x. What did I have? Negative 3x plus 3. Remember, you have to factor out this omega, and this would become x minus 1 to get your shift. So if you're going to use the even odd property, you have to get this omega factored out. Then you could change this to just 3x minus 1. But you could not do cosine and just drop the negative on the 3 over here and say it's because of even property. All right, you can't do that because you have to factor this omega out, then do it. All right, then if you put the 3 back in, you'd get cosine 3x minus 3. See, this would make you off by a plus or a minus. So make sure you put it in that form where the omega is factored out of the phase shift before you use the even-odd property if it has a phase shift in it. Now, if it doesn't have a phase shift in it, you don't have to worry about it, right? If you got y equals 5 cosine negative pi x plus 5 with no phase shift, that's going to be exactly the same as 5 cosine pi x plus 5. Now you could just get rid of this negative because of the property that it's an even function. All right, guys. Well, I hope that helped, and this should help with your graphing. I think you've got a couple of them in there where you have negative phase shifts, or excuse me, negative omegas, and so you need to use your even-odd properties to handle that. And then you have a couple more of these lovely sinusoidal curve fitting things to do. And I hope you have a good weekend. Email me if you have any questions. So just to be clear, sorry, I do want you guys to do the amplitude, the vertical shift, and the period of the other two by hand and see what you would get. Write it out just like we did on this slide. Then you could go over to Desmos and compare with Desmos and see what they have, and you could use Desmos to figure out your phase shift. And then you could write your final answer, something like this. So here's what Desmos came up with. Here's what we came up with. If Desmos is different than us, I want you to kind of explain like how those are the same. If it's close, you know, I mean, we would expect some of these to be close, like 3.15, 2.94. You don't have to explain why those are different, right? They're close to each other. But if Desmos does give you a negative omega, I want you to kind of mess with that and see what happens there. I want you to compare what Desmos is giving you with the problems that we came up with. And then you're going to have to use Desmos to determine.